Welcome to MEI Numerical Methods, Solution of Equations 1. In this video we'll be looking at the Newton-Raphson method. So here we have a general curve and we're trying to find the point where the curve crosses the x-axis as usual, and suppose that we choose x0 as our first estimate. Then we draw a tangent to the curve when x equals x0 and continue the tangent until it meets the x-axis. So that gives us the value x1, which, as we can see in this case, gives us a value that's closer to the true root than x0. Now, in order to obtain a formula for x1, we note that the gradient of the curve when x equals x0 is going to be f dash of x0, which we can work out, and that's the same thing as the tan theta, which in turn is equal to the distance up divided by the distance along, which is f of x0, which is that distance, divided by x0 minus x1, which is that distance there. So we can see that x1, which can be written as x0 and then subtract that amount there, so we're taking off that amount to get from x0 to x1, and from the formula we've just established we can see that x0 minus x1, so just rearranging that relation there, gives us f of x0 divided by f dash of x0, and this is the Newton-Raphson formula. So now we're going to look at the example that we've been considering with the other methods. So as before, we're trying to solve the equation f of x equals 0. So we've got the graph of y equals f of x, and we're now going to apply the Newton-Raphson method to this. Now, it's quite easy to apply the Newton-Raphson method using a calculator, and we're going to take as our initial estimate 1.5. So there we have the Newton-Raphson formula, and we're going to need to know the derivative of the function, so that can be worked out easily in this case. And as we saw in an earlier video, we can use a calculator as follows. So we're going to type in 1.5 equals, so that the calculator knows that that's what it calls the answer. So, and I think it's a good idea to press the all clear button at this point. In fact, you may need to do that. And now we're going to type in our formula, but instead of x0 we're going to have the ans button. So that x0 there becomes that ans there, and then fx0 up there. That's our function f of x there. So that is just becomes ans cubed minus ans minus 1, and then in the denominator we're now using the derivative, but with ans instead of x0. So once you've typed that in, and then press equals sign once to get your next estimate, i.e. x1, and then repeatedly to get x2, x3, etc. So you might like to pause the video and try that for yourself. So hopefully you've got these values, and we can see that the convergence for the Newton-Raphson method is much quicker than for either the bisection method or the false position method. But now we're going to look at a case where the Newton-Raphson method fails, and because we're dividing by the derivative in the Newton-Raphson formula, we're going to find a place where the derivative equals 0, i.e. a stationary point. So we've got the derivative as being 3x squared minus 1, so setting that equal to 0 means that we want x to equal 0.57735. Now in this spreadsheet we've worked out the iterations for the Newton-Raphson method using 4 different start points. So in the second column, with a start point of 1.5, this is what we did before on the calculator, and once again we've got the value of 1.324718 to 6 decimal places isn't changing after the after x3. Note in passing that if we had a value of x0 which was a bit further away from the true value, but not ridiculously far away, it varies by function, but in this particular case it does take a very long time to settle down to the, we can see at the end of at the bottom of the screen we've got 1.32492, which is getting reasonably close, and it will actually, if we carried on a bit further, it would actually get down to the 1.324718. But if we choose a value of the one we were looking at a moment ago, where we've got a stationary point, obviously this is only at the stationary point to 5 decimal places, but we can see that if we were to plug in that actual value of 0.57735, then we're not really making any progress at all. I mean, maybe we've gone down from 6.24 times 10 to the power of 15 for x1. It's gone down a bit by the time we get to the bottom of the screen, but it's still a huge number, so to all intents and purposes it's not working. But notice, however, if we were to change our value just very slightly, so we've added 0.001 to get to 5 decimal places, we've got 0.57835. Although it does take a very long time to settle down, the numbers aren't anywhere near as large as they were in the previous column, and we can see at the bottom of the screen we are actually getting down to very close to the true value. So in summary, we can see that the Newton-Raphson method breaks down if x0 is near a turning point, and something else that can go wrong is if our value of x1 has been carried too far away from the true value, and so much so that it's actually outside the domain of the function, because then of course we can't continue the process because the function won't be defined for x1. Alternatively, x1 may have been carried far away from the route that we're interested in, and it might go to another route, one that we've already found. So that concludes the video on the Newton-Raphson method, and we'll be looking at the secant method in the next video.